We are Lidar's research group, and we welcome you to Industrial's affiliate program. Lidron is composed of computer and electrical engineering students, and it's divided in 4 groups. In our architecture group, we have our leader, Ana Ortiz, with her members, Samuel A. Diaz Vidot and Daniel Torres. In our obstacle avoidance group, we have as the leader, Gabriel Figueroa, and his members, Rafael Alvarez and Jorge Torres. In our sensors group, we have Omar A. Rodriguez, and in the outreach group, we have Emmanuel Rivera, and I am the project manager of Lidar. Lidar's mission is focused on integrating LiDAR sensors on an unmanned aerial vehicle. Lidar is developing an autonomous landing algorithm capable of detecting, deciding, and comparing risk when finding a possible landing zone. Our system will use the integration of sensors such as Leddar 1, Leddar M16, Intel RealSense camera, PX4 flight controller, Odroid XU4, and Veloline Puck Light, mounted on a Tarot 680 Pro. Our implementation consists of initializing our drone, locating the waypoint on the GPS, turning on the camera and 3D LiDAR, facing the waypoint, flying to the waypoint on a straight line, and if it encounters an obstacle on its path, go over it or around it, and continuing on its path until it arrives or finds another obstacle. Once it arrives at the waypoint, it will be scanned rotating around the circle, and once it decides how many possible landing zones are within this circle and which is the best, comparing between slopes and objects close to this possible landing zone, it will move to the area and start descending while rotating, capturing any objects that can sabotage our landing.
Together with the architecture group, we obtain information on how to extract the data from the LiDAR sensors and manipulate it to manage the drone's orientation. LOS contains a library named TF2, which lets the user track a multitude of coordinate frames over time and transform points and vectors as an example between any 2 coordinate frames at the desired point in time. Through the TF2 library, all information about the coordinate frames are available on all LOS components on any computer in the system. The TF2 library can operate with a central server containing transform information or every component in the system built into its own transform information database. Our PX4 contains a proportional integral derivative controller which can obtain gyroscopic data to representation of Euler angles, which can bring the orientation of the drone. In essence, pitch, yaw, and roll angles. For future work, the TF2 library can be implemented to extract the Euler angles of the drone and transform these values into quaternions using the TF2 library to obtain a more precise result, as quaternions can be represented as matrices to perform computational calculations when we implement the safest landing zone algorithm in the future.
This semester, the obstacle avoidance and detection team worked with flight planning. Our objective was to be able to create simulations that show the behavior, the data, and the efficiency of components using the open-source 3D simulation software Gazebo. In our research, we found that we can add plugins of specific components and models that can aid us in creating a more detailed simulation. That way, we can test the efficiency of the system in a safe environment, all while receiving important data with great precision. For this task, the group completed tutorials and did research on how to use Gazebo and other necessary software, such as Rasnoetic, Mafros, and Cube Ground Control. With this, we were able to run a simulation in which a UAV follows a custom path at a designated altitude. Our next step is to use flight planning to help develop a functioning detection system for the UAV, using plugins for a depth camera, which in our case would be the Intel RealSense D435. Ultimately, our goal is to create a robust obstacle avoidance system, and with flight planning we will be able to develop it with complete safety. Flight planning will also aid the other groups in testing the effectiveness of their systems.
The ROS architecture team had various goals for this semester. Our first goal was completing a PCB development design to connect the components together to form a working circuit. From this, we calculated the time of flight and battery consumption needed. After these calculations, we noticed that a new battery was needed in order to divide the voltage intake and divide battery consumption equally. This objective is still a work in progress as it depends on the communication with the supplier and the availability of the product. Our second goal was choosing the architecture. Event-driven architecture was chosen because of decoupling of producers and consumers. Similarly, ROS also decouples its data. It is better for real-time development, and event-driven also includes microservices, which focus on creating various tiny programs and then creating another little tiny program every time a new feature is needed. Further progress was made by the findings of the TF2 and CV Bridge packages. These packages focus on letting the user keep track of multiple coordinate frames over time and converting between ROS image messages and OpenCV images respectively. Finally, a PX4 simulation with ROS, Gazebo, and Arvis was achieved, more specifically the Velodyne POC. The simulation was achieved by running a ROS launch command to launch various nodes to publish and subscribe to different topics, which can be seen using Arvis. In this case, we focus on the Velodyne points topic. We also observed how the point cloud data could be visualized at different altitudes and angles to recognize the varying perspectives that could be observed while the drone is in the air.
For any questions, you can contact us via email. Thank you for all your support.